So, uh, in today's video, like we are here for a very interesting topic. So, one of our viewers requested us to talk about AI agent harnesses, and we are thinking like what topic would add the most value when it comes to AI agent harnesses, and that led us to a tweet by Alex Zhang where he talks about RLM. So I'll just share that tweet, and like that is a very interesting tweet because it talks about what Opus 4.8 bring brought up with their capability. So something that surrounds with dynamic workflows, which Claude recently launched, wherein you break a single task into multiple subtasks and you assign sub-agents to each task to complete that unit of work, right? So all of this happens dynamically, and this tweet really captures uh, the topic that we are going to talk about. So I'm just sharing my screen. Okay, so here you can see Alex Jang talking about RLMs, which is recursive language models, and its relationship with dynamic workflows, which Claude recently introduced, right? Also, Omar Khattab mentioned about RLM sometime back about, hey, like RLM problem is solving limitations of compaction, and there is some tweet retweeted of Alex Jang. So, yeah, so today we are going to talk about RLMs, what RLMs are, why they are so special. So, even before diving deeper into this topic, right, like let's try to visually understand uh, what what RLMs are and how they differ from our simple LLM calls. So, let's try to see a tiny demo. So, sharing my screen over here. So here you can see we have a very small context. What is 2 plus 2? And you have a question that is corresponding to the context, like answer in one word, right? So let's try to run simple element, see what answer we get. I think it was already set. Yeah, okay. So we have the answer over here. It will show you number of tokens consumed, and we have the answer. Now let's try to do the same thing for RLMs
Can you let
and
Sati
see
go?
what has happened.
Okay.
Yep. So
Yeah. Fine.
you're saying,
Yeah. So this one is RLM, right? This is RLM working.
yeah, yeah. Hmm. Yeah, so um, here you can see a job has spun up, right? And there is some configuration associated with it, and there is some long prompt that is given. There is something related to REPL over here, and eventually you try to print some answer and get some output. Okay. Okay. Oh, sorry. Okay. And here the final answer is being written. And if you see over here, the amount of tokens that it took to answer a very simple question is way too huge, right? So we'll be diving deeper into what RLMs is and like what each of these iterations mean. But let's try to bring our heads to, hey, there are some tasks where simple LLMs make sense, and there are some tasks where RLMs make sense, right? So for a very simple task like answering what 2 plus 2 is, uh, simple LLM will just get the job done, right? In RLM, uh, yeah, RLM is for much more sophisticated use cases. We'll talk about what kind of data uh, RLM makes more sense.
Hmm.
Okay, so Abhishek, so this is a question for you.
Mm-hmm.
So let's try to brainstorm on this one for a bit. Okay.
Mm-hmm.
So we have a list of questions,
Mm-hmm.
and each question is of some category. Okay.
Mm-hmm.
And this category is what you want to predict for each of these questions. There are like hundreds of thousands of questions that are being given to you, right? And each question is having some category. And at the end, you also need to output what is the maximum count, uh, what is the category that is occurring most of the times in the entire data set.
Mm-hmm.
That's the task given to you.
Mm-hmm.
Okay. So yeah, let's try to brainstorm on this. Like, how would you go about this problem statement? A very simple problem statement, but yeah, let's try to think of it.
So I'm assuming I'll have some defined categories, let's say 10, 20 categories. And then I assume I'll have clean data. If I don't have clean data, then I'll clean that data.
Yep.
And then I'll just write a prompt, very simple prompt, which can be done in single LLM call. And I'll fire that prompt
Hmm.
in a for loop for, 1,000 times, as many questions are there, and just simply ask
Correct.
LLM. And
Hmm.
then and then since we need at the end like some metrics on which are the most often occurring uh, classes, classifications, and categories, then we can use some counter over it.
Just do a simple count.
Yeah.
Exactly. So Abhishek, like very nicely put. So, as you mentioned, like there are two passes that you need to do through a data, right?
Yeah.
So first is the pass where you classify questions into some category. Second is the pass where you count those categories. So these two passes are exactly where LLMs shine. So these are called as O of n square problems in the terminology which RLM brings. So, yeah, let me just share my screen over here. Okay. So over
Perfect.
here we can see, yeah, over here we can see O of n square problems. And this data set is called Oolong. We'll try to see an example of this data set and what exactly this data set is. Okay. So let's switch over to a new tab. I'm just copying the example over here.
Awesome. This is
Okay,
nice.
yeah. So here we can see that the first few lines say these are 787 general questions, and
Mm-hmm.
there are six defined categories for each of the question, right?
Hmm.
And you will be asked to aggregate label statistics across these examples, okay?
Mm-hmm.
And one of the questions which I just asked you, Abhishek, is like, what is the most occurring label, right? So here
Mm-hmm.
in this case, what does IOC stand for? This is a question where abbreviation is the expected output, right?
Yeah.
Um, Similarly, what do the letters in DC stand for? That is again an abbreviation. Okay, so let's try to think of like where it would go wrong when it comes to LLMs, right? So, in case of LLMs, you are trying to predict next word. In one single pass, you are trying to do two tasks. One is identifying the
Label.
category,
Yeah. Yeah.
category or the label of the question, and
Yes.
then you are also trying to keep in mind a number associated with that label. So, for
Yes.
a single LLM call, doing both of these things in the same go, it becomes very, very difficult, and you tend to lose the track of these label counts. So simple
Yes.
LLM call will fail drastically in this kind of scenario. So
Also, right,
let
like we remember
yeah,
the example of strawberry, right? They can't
yeah,
count the LLMs are not good at counting. So they have hard
yeah,
time counting R in strawberries. So that's not the case these days, but in general, the for the second part of this problem, when we have to count the labels and the categories, ideal
yeah,
way is to write a Python code for it. And
exactly,
yeah, rather than
yeah,
relying on
uh,
LLM that it will do do the right counting. And
yeah,
uh,
yeah.
yeah, so usually how I would go about this if I don't know anything about RLM is that I'll just ask it to write all of the outputs to a file and then later read that file and then uh, you know
Then try to count it.
then try to count it using that file, load that JSON, maybe later on and then do it.
Correct, correct. Cool. So let's try to see how RLM handles this kind of data set. And let's try to dive slightly deeper into what RLMs are. So without further ado, so here, like this is one of the examples that I have already run. Let's just look at the outputs. So for the data that I showed you, right? Like I have loaded mini Oolong. Like basically, it's instead of 787 questions, it's just 20 questions. Just in the interest of time, I have kept it short. Uh, so here, let's try to see how simple LLM call performed. Okay, so here, simple LLM generated 2000 output tokens after reading the input prompt, and even then, it could not generate any meaningful content. Right?
Yeah.
It could not give you the answer. So that is one thing that we saw. Second thing is how RLM came across it. It it went through a lot, right? Lot of prompt tokens, lot of output tokens, but here we have gotten a specific answer. It took around 260 seconds for this, and let's try to dive into RLM and what steps it took to arrive at this answer. Okay.
So the two
Yeah.
questions. One
Mhm.
is like,
Mhm.
was the original context having 20 questions or just one question?
So here, uh,
Can you show us the
the
prompt?
question, the set of questions, yeah.
Uh-huh. Yeah.
So over here, even though it's mentioned like you will have 77 examples, I have trimmed the number of lines.
Okay, sure.
Okay.
Yeah.
So
And then
yeah,
what is
so
the
these are
prompt?
like way lesser question. And
Sure.
over here, what is the most common label?
Right, right.
Okay.
So the
Give your
answer
final answer.
is the answer is obtained after like counting and getting the max
Counting.
basically.
Yeah. Yeah. Yeah.
Understood.
Exactly.
Understood. Cool. Let's
Okay.
go back and see
Cool.
the RLM stuff.
Yeah, let's try to look into each iteration, what it's trying to do. We'll go through its prompts and basically everything right now.
Sure.
Okay. Um, yeah. So here, let's try to focus on, yeah, let's try to focus on this part wherein, uh, wherein RLM is being instructed to use Python REPL. Okay.
Mm-hmm.
Here, okay, it's here. To use Python REPL, you need to write code blocks in REPL format.
Yes.
And there are some queries and like some functions available. Okay, LLM query, LLM query batched, and these are basically showing variables, answers, and so on. We'll just skim this prompt through. But one thing which we understand over here is this entire concept has some environment to interact with, right?
Yeah.
And the context is to be interacted with RLM.
Yeah. Yeah.
Context is to be interacted with the environment.
Python REPL, right?
Yeah, Python REPL. Yes. Okay, I'm just going to scroll through a bit. Yeah. So here, uh, let's देख रहे हो क्या?
Yes, yes.
हाँ
This is visible, yes.
ठीक है. हाँ नहीं आप नीचे देख रहे थे मैं रुक गया था थोड़ी देर के लिए.
नहीं नहीं मैं नोट कर रहा था कुछ कुछ.
ओके ओके ठीक है ठीक है. Cool. So here we can see that there's a user prompt wherein we are saying ki you have not interacted with REPL environment and seen the prompt or context yet. Look at the
Mm.
context first. Do not provide the final answer yet. Okay.
Mm.
So here RLM is being specifically instructed to interact with an environment. Okay.
Yeah.
So if you see what LLM has come up with, first it is trying to understand the length of the context.
Yeah.
Then it is also trying to understand type of the context. Here it's trying to identify what first 500 characters of context are, right? So, and at the end, like it got the output of whatever REPL code it has generated. Okay. So, let's just pause over here for a bit and let's try to draw some parallels around how Claude code Claude Code does its thing, right? Whenever we attach some data.csv, what are the things that you see happening, right? It does a lot of grep. It does head minus 20. It tries to see
Yeah.
some parts of data
Yeah.
and it tries to understand, hey, like this is how the data is structured. Now I'll try to build on top of this. So something very analogous we are seeing over here in RLMs.
Yes,
Cool.
yes. Yeah, I think
Yeah.
if we have some traces, we'll show them next time, right? I think I've seen this
Yeah.
very often that if you give a large JSON or something, it will write a fancy JQ something and just look at
Yeah.
top five keys or something like that.
Exactly. Exactly. So yeah. So that's where I think our harnesses and RLMs are very close. So that's what we have understood so far. At this point, I think it's best to take a look at what is the architecture of RLMs. So in simple LLMs, right, you have a query, you have some context, you feed it to LLM, and you get the result as an output.
Perfect.
But in RLM, it's slightly different. You give in the query, you feed the context, but your LLM, in this case RLM, does not consume context in a normal manner. The context is stored as a variable in some environment, and the only way to access this environment is through Python code. So that's where REPL environment comes into picture. So this context lives as a variable inside in this environment, and you are free to do string operations like looking at the first few characters, checking out the length of this variable, trimming it down, splitting it. Imagine every Python operation that you can do on a variable, you can do it in this environment,
Yes.
right? So also there is one other special thing you can see over here, right? So there are some variables which you can keep intact um, in this environment, right? So you can write sub results of your process that you're going through into these variables, and you can keep on consuming them, create multiple new variables, and then give the final answer. So even while giving the answer, right, you are not giving it directly; you are giving it through some variable. Okay, now
Yeah.
let's try to look at the diagram which we have over here. So here you can see RLM is an LLM in some special environment. Okay,
Yes.
so LLM interacts with the REPL environment to access the context that is available. So one crucial point I think we missed is RLMs are very good at handling large context, right? So
Yes.
if some model has a limit of say 262K tokens, right? You can feed in like 10 million tokens, 1 million tokens, and it will still be able to go through it, right? So, and we'll see how it goes through like lot of context in the uh, upcoming few moments.
So just to have an intuition, right? This is possible only because you're not looking at the context directly. You have all the context and all the sub results as variables, and you are only manipulating variables at this point. So the context window of original LLM has only the variables and only the Python code mostly. All the sub work
Yeah,
is in a REPL environment. So all the computations,
exactly.
all the state management and everything, this is not polluting the main context, basically.
Exactly, exactly. So if you were to do it in an LLM, you lot of your memory would have been wasted in managing these states, these variables, right? And it would have become much, much difficult. So imagine a harness, right, wherein you are doing lot of these greps. So all
Yeah.
of that is happening on the go, on the fly. It is
Yeah.
not reading through your entire context of data. So very similar thing is happening over here as well. And you rightly pointed, that is what enables these special LLMs to not pollute their own memory.
So if I think
Cool.
about it differently, the gist is that RLM is like an LLM in an environment. Here, the environment has happens to be a Python REPL, but file
Yes.
system could be just one of the environments, right? So what I could do potentially is have the context in a file, read it in a very well, write some Python, read it, do some processing on it, and then
Mm,
write results back in a JSON. And then
yeah,
later read the JSON, do some processing, write a new JSON. So that way in my directory,
exactly.
I have many small files, each of them. I know the file names, I know what they contain as an
Mhm.
LLM. So my context window is not filled with the content of the JSON, but I still have a pointer to those files and I can use file system as an environment instead of just Python. So there are like more
Exactly.
possibilities.
Exactly, exactly. So here in this case, it's in memory. So
Yeah. Yeah.
in the example that you gave,
Yeah. Yeah.
that's
Yeah.
written to some file system.
Yep.
But
Yep.
yeah, like in RLM, it is in memory.
Yeah.
Thanks for bringing that up. Cool. Let's move on to the next iteration. I think it will make much more sense as to what's happening now. Now, let's try to look at the second iteration. In the first iteration, we tried to see what type of data it was, what were the first few characters of it, basically get some idea of what data we are dealing with, right? So uh, this is the first iteration that happened once. And now let's try to dive into what second iteration is doing. Okay, so as an input to second iteration, all the code that was written earlier and all the outputs of that code are appended to this prompt. Okay, so here you can see LLM prompt this turn.
Yeah.
Okay, and for this this turn, now it started to think on what's next. Okay,
We can
so
also see
it's
the
now trying
variables,
to
right?
print.
We can also see the
Yeah,
variables.
exactly.
Yeah.
Yeah, so answer context zero. So these are some variables which are LLM created.
Yeah.
Okay, and yeah, so here it's trying to print the entire context. Now let's think why it did this, right? Why did it print the entire context? So here 20 questions is not a lot, right? Here 20 questions is like very few characters, and it is very well it can very well fit into the memory, right? So it has printed that entire thing to understand the data. If it was if it was very lengthy data, right, 700, 800 lines, it would
Hmm.
have chunked it into smaller pieces and then tried to make sense of data. But because this is a dummy example and very small one for that matter, it has printed the entire context. Let's just try to go to the next iteration and try to see what it's doing once. Yeah, it's third iteration. And in this iteration, it is now trying to identify categories for each of the extracted questions. Because it had already printed the entire thing, now it's trying to assign some labels to it. Okay. So here the code got executed.
So
Let's try to
I think it
see.
did it in one shot and just printed the entire
Arey
list of
ha.
20 things. But the good part is that it stored them as variables for a computation later, which would not be possible otherwise. All right.
Okay. So here we have come up with a better example, slightly longer example to point out how exactly RLM works. This is a better example. So we are tracing each of the iterations, and uh, as we saw in iteration one, we tried to get what type of context it is, what is the length of it, and so on and so forth. Once we have some context of what data is, the next thing that we do is we try to check even few more sections of code and try to get more sense of it. Because it's slightly longer context, you check if there is some discrepancy in the data that is next. So we do the same thing over and over again. So here you can see each, you are not ingesting context entirely. You are just checking chunks of each of the context and then trying to devise the plan, right? So let's skip iteration three and four because it's trying to do very similar things. and just take a look at what iteration 5 is doing. Okay. So here, as you can see, we are extracting first 100 lines of question. Okay. And then we are trying to print it. So something that we would do in uh, do it while doing the entire thing manually, right? So here you can see each line. So this has been broken down into 5 questions each.
Yeah,
Okay.
chunks of five. Yes.
Okay. Yeah. First 5 questions, then it's second 5 questions.
Yeah, I think those
Let's
are
try
first five
to
lines.
understand.
I think it has
Huh.
empty characters, empty lines in there as well. Uh, yep, yep.
Yep.
So it
Over
has
here.
just taken lines, and those are like total 106 lines, right? But the question set is
Yeah.
100, so there are like few empty stuff it has taken up.
Okay. Moving on. Let's try to see what it has come up with next. Okay. Let's see the thinking part.
But
The
now
actual
you
question
see
lines
the
start from
variables.
index 1.
If you have variables, right? First
Yeah.
100 is new lines, and first 100 is now those are two new variables in this demo, right? So it
Yeah.
has broken down the problem into 100 chunks, and then it will solve them accordingly. And that is a
Yeah.
variable it has.
Yeah. So instead of interacting with the entire context, now you just have to think of one single variable. So instead of thinking of 100 different questions, you have one variable to interact with. And also, like, this is one interesting point, right? Like, it thought about there are some header lines, right?
Yeah,
There are 4 header lines,
yeah,
and it decided to remove it.
yeah.
Okay. And then it's trying to go through each of the question. Okay, so let's try to see. So yeah, eventually it executed the code, and now we
Data
see
cleaning.
uh, yeah, cleaned up data, and now it will try to do something. Let's see. Let's see what it tries to do next. Okay. So check what's in lines 100 onwards. Okay, fine. It's still checking out the data. Let's skip that. Yeah, iteration 8. Okay, now it's trying to clean up these lines,
Regex.
pipes and
Yeah,
instance.
yeah,
So,
yeah, yeah.
yep. So it's also doing the cleaning for you. Okay.
Yes.
And it tried to print the entire thing for you. Now let's try to look at
It printed only five, right? It just wants
ninth
to
iteration.
see what the output sample looks like. It
Yeah.
just printed the five. You see,
Yeah.
like it enumerated until questions five. If you see like one above, one chat window above.
Mhm. Yep.
Yep,
This
it
one.
just printed five. So it's getting smarter.
Hmm. Yeah. So cleaning it tested only on 5. So I
Yes.
think that's fine because it had already taken into account like some chunks of your data. Okay.
Yep, yep, yep.
And let's try to see this now. This is something interesting. So here it directly gave a prompt. Hey, like these are 6 categories, and these are the questions that you have, and this is how you are going to classify them. Okay, so this is the prompt template. Okay, this is the prompt template,
Yeah,
and over here you're trying to do LLM query
LLM
and
query.
then prompt.
So this is your original LLM deciding to do an LLM query, right?
Hmm. Yeah, exactly. So let's just go to whiteboard once again. So in RLMs, there is something called as root LLM, and there is something called as sub LLM. So the role of this root LLM is to write code. Okay. And the sub LLM will do the execution part. Something
Yeah,
very analogous to our agents, right? Wherein you do the heavy lifting of writing a good prompt, setting up the context for sub agent to work on. So here in case of RLMs, you are setting up context for sub LLM to work on. So root LLM is not doing the classification part. That is being done by sub LLM.
yeah,
So here you your root LLM calls a special function called as LLM query, which then triggers a sub LLM, which then classifies those questions for us. So
Yeah.
let's get back at demo and let's try to see that in action. Okay.
Yeah.
So here you can see LLM query is a special function that is being called. So this special function is available in the environment and that gets run in that particular environment. So the root LLM uh, does not does not consume all of the context over here as well. So a lot of offloading of tasks is being done. Okay. So here you can finally see there is some answer that has been emitted. Okay.
Yeah. I think, can you zoom
Okay.
in a
Yeah.
little?
Ideally, there should have been an answer variable in which data gets stored. The demo glitched at the last moment, but yeah, over here, if you see, uh, the answer is stored. This is a different demo, but yeah, here the answer is stored in some special variable. Okay. So here answer content equal to the final answer. And this REPL environments variable serves as the final output in the entire prompt. Okay. So here you will get something of this sort. So yeah, that's for the demo. Uh, let's go back to our index. Yeah, and let's try to summarize what we just went through and like where the differences of LLMs and RLMs come into picture, what their architecture is. Yeah, Abhishek, would you like to summarize this for our viewers slightly?
Yeah, I think my key takeaway was that RLMs work with an environment, and if they have access to that environment, then they don't need to process all of these things themselves, which means they can process contexts which are way longer than their context window without messing up the outputs.
Hmm.
We tried to show that
Yeah,
via like two demos, and hopefully we communicated the fact that there is one LLM query that root LLM itself decided to call, and then the variables that it stored, then it did a computation over it to find the max and then return the result. So,
yeah,
and I think that's also the basic scaffolding behind Claude dynamic workflows, that they defined a workflow.ts like file, and then each of those steps is an LLM query, like an agent in themselves. And the way
exactly.
orchestrator works really well is because orchestrator does not have to keep the context; it just has to maintain those the TS file and their states, basically what is done, what is pending. The similar idea that we
Correct.
were saying via file system, that could be an environment as well. And
Hmm.
off late, we have seen a lot of RL environments are being spun up for robotics, for code, uh, and the way LLMs reason about when they have environment is very different from when they reason when they have raw data. And I think the key point here is that the symbolic reasoning, the reasoning over the variables, which is
Yeah,
reflected in their Python code, the nested loops, ifs, and else. And I think it is very, very terse and precise to express all of that symbolic logic that, hey, this is a variable, this is a list, and I want to matlab, take the max count. And all of these things are very precisely done in Python and not in English. So
exactly.
whenever we give
Right.
instructions to LLM, they think in English, right? That's a markdown instruction. But if an orchestrator is thinking in terms of symbolic uh, variables, variables, loops, ifs, then it's doing a very precise thing that it's very good at, which means
Exactly.
if it's not bloated with the raw markdown, then it can do a lot of wonders. And then all of the heavy loading is given to sub LLMs.
Right. Right. Very nicely put, Abhishek. So the other point which I wanted to talk about was difference between RLM and RAG, right? So we saw that RLM was going through a lot of chunks, right? It
Hmm.
was trying to look at parts of data in each of the iteration, and it was trying to come up with what next steps should be. In RAG, we also do a lot of chunking, right? We do a lot of chunking, and we eventually do a query. We try to retrieve and try to come up with some answer
Yeah.
based on these chunks, right? So one thing to note about RAG is that RAG has very hard-coded way of creating these chunks. You might break a chunk after a paragraph, after first few hundred characters. But over here, you must have noticed that RLM does chunking uh, in a manner which is very dynamic in nature, right? It will
Yeah.
try to look through the data, and based on that, it will try to do chunking. One very important thing which RLMs also do is they do sub LLM calls, meaning each of the chunk can be operated on by a separate LLM. So very
Yeah.
analogous to how multiple sub agents work in agent harnesses, right?
Yeah.
So that is
Correct.
one thing that we should take a note of. And yeah, so that is mostly it for the RLM part. I think we should just stop over here, and I hope this video helped you understand a brief idea, give you a brief idea of what RLMs are, and feel free to drop in comments and help us help us with what you want to see next. We'll happily cover the topics for you. Okay, that's all. Thank
All
you.
right.
See you.
Bye
See you in
bye.
the next one.